Why does the quantum physics need an interpretation? Why was there a dispute at all between Einstein and Bohr? So, quantum physics needs an interpretation because it's not immediately clear what the theory is saying about the world. Mathematics of quantum physics is unfamiliar, and connection between mathematics and the world we live in is hard to see. Newtonian physics describes the world in a familiar and simple world, in a world of 3 dimensions filled with solid objects that move in straight lines until something knocks them off at their path. The math of Newtonian physics specifies the location of an object, a set of 3 numbers, one of each dimension, known as a vector. But quantum physics is significantly stranger than Newtonian physics, and its math is even stranger. So, if you want to know where an electron is, you need more than 3 numbers. You actually need an infinity of them. Quantum physics uses infinite collection of numbers called wave functions to describe the world. These numbers are assigned to different locations, a number for every point in space. Everything has a wave function in quantum physics. The chair I'm sitting in, the seat I'm sitting in, even you watching, the atoms in the air around you, electrons and other particles inside those atoms. An object's wave function determines its behavior, and the behavior of an object's wave function is determined in turn by Schrodinger's equation. Central equation in quantum physics that was discovered in 1925 by Erwin Schrödinger. This equation shows that wave function always change smoothly. The numbers inside the Schrödinger's equation flow perfectly, predictably, 5.1, 5.2, 5.3 and so on. A wave function's numbers can go up and down again like a wave, hence the name wave functions. But they move smoothly like waves, never jerking too crazily. Wave functions aren't too complicated, but it's a little weird that quantum physics needs them. Newton could give you an object's location using only 3 numbers. But quantum physics needs an infinity of numbers scattered across the universe. The wave function doesn't tell you how much of an electron is in one place. It tells you the probability of an electron is in that place. The predictions of quantum physics are generally in terms of probabilities, not subtleties. Certainties, and that proves that Schrödinger's equation is deterministic probability. So probability doesn't enter into it at all. You can use the Schrödinger's equation to predict at perfect accuracy of how any wave function will behave forever. But once you do find the electron, the funny thing happens to a wave function. It collapses. It instantly becomes 0. The equation holds all the time, except when you make a measurement, at which point the Schrödinger equation is temporarily suspended and the wave function collapses everywhere except at one random point. This is so weird, and it gets a special naming, and its proper name is called the measurement problem. But what counts as a measurement anyhow? What is a measurement, and how do we solve it? Does it require a measure? Does the quantum world depend on an audience? Can anyone collapse a wave function? Where's the divide between the quantum world of the small and the Newtonian world of the big? It's disturbing. Yet, despite all the weirdness, quantum physics has been widely successful at describing the world, much more so than simple Newtonian physics, which was already pretty good. Quantum physics, well, we wouldn't have any understanding why diamonds are so hard, or the electronics. Wave functions with their numbers casually scattered around the universe can somehow be related to how we see the world. Otherwise, quantum physics wouldn't be any good at making predictions. What is a wave function, and how is it connected to the objects, and how it is connected to the world around us?